Hello, welcome everyone, and good morning, good afternoon, good evening, wherever you are and whatever time you are listening into this online presentation. My name is Uday Masurekar. I'm Senior Director, Telco R&D, VMware, and I have with me Mike Beadle, who is Director of Engineering, Intel. And today we are together going to walk you through the high-performance vRAN platform, which is empowered by VMware's Telco RAN and Intel's FlexRAN solution. As you probably know, Intel and VMware have been working for years in the server virtualization market, bringing more and more advances. Today's presentation, however, is going to focus on one of the new technologies, new areas, new industry, which is vRAN, and how Intel and VMware have worked together for last 2 odd years, how the R&D groups from both the companies have had this joint collaboration. I and Mike will talk you through the journey that we have had, the experiences that we learned, and the products and the solutions that we have built. So with that, I will move on to the agenda. The overall presentation will be within the 4 high-level sections. In the first section, I will talk through the overall telco cloud hierarchy. Then I will pass it on to Michael. Michael will talk through the Intel solutions, FlexRAN, the software solutions, as well as the optimization considerations that one need to introduce and implement. And then I will take it from there. I will also talk through what are the performance knobs or other configurations that one needs to employ, what are the challenges with respect to cloudification or virtualization, and how VMware TCP RAN solution tries to address those. Lastly, we will summarize with where we are, where are the test results, and what do we want to do in the next few months and time to come. With that, I'm just going to walk you through the overall telco hierarchy. For any opco, what you would typically see is the overall telco deployments are more like a hierarchical tree-like structure. On the top, you would typically have the OSS, BSS functions, which I'm showing here more on the left-hand side. That's where you will have most of the management and automation functions residing. These are the perfect candidates to be hosted in public clouds or in the industry standard virtualization platforms. As you start moving towards your right, you will see that then core elements start coming in, something like subscriber DB or Kalia and few others. You still can have, they of course will have additional requirements as against their counterparts on the left, but yeah, they still are eligible to be hosted on public cloud as they don't have as much of resource requirements. Today's discussion, however, is going to be more on the rightmost side of this picture, where we'll be talking about some of the RAN components which are more closer to cell sites, and these include the DUs and CUs as prescribed by the ORAN technology. These components, as against the other components, are very resource intensive. They expect some stringer functional as well as performance SLAs to be met from the underlying platform, and the overall platform needs to deliver that, not just from the functional perspective but also from the automation and optimization perspective. So telco solutions from VMware provides first the platform which enables this, and also the automation. I'm showing that on the top section here, which is called Telco Cloud Automation, which operates at all the layers all the way from left to right and enables this configuration. And with a joint collaboration with Intel, we also have this automated CI/CD pipeline that we will talk in subsequent slides, which helps to aggregate all these components, all the moving parts, and make sure that the RAN vendors, and not just the RAN vendors, but also the service providers and system integrators, can have a peaceful mind that all these things are working together, both from functional as well as from the performance perspective. So with that, I will move the slide to the next topic, where Mike will come in and talk through the Intel solutions. Over to you, Mike.
Thank you. First, just some context on FlexRAN solutions. So what is that? It's a hardware and software reference implementation that enables customers and partners to implement vRAN solutions on Intel silicon. That includes the CPUs, typically accelerators, whether that's FPGA or EASIC based, and NIC cards. And then the software piece of that is reference software that has fully featured and based on 3GPP standards for LTE and 5G. It serves in multiple purposes. One is it's a reference solution so people can see how to implement and get the best performance on Intel hardware. It also is a way to identify best practices and optimizations that'll ensure the best performance, whether it's cycle count or wireless performance. And this evolves over time. We typically release on a quarterly cadence. And that software is provided in kind of a modular and a full pipeline view. So it can be used for end-to-end testing, but it can also be used in a piecemeal approach where customers or partners can pick up segments of that code or libraries and integrate that in with their own implementation. It's a broad spectrum, all the way from macro to small cell, and supporting sub-6 millimeter wave for 5G. And so it's basically can address kind of any of the base station markets depending on the use case and opportunity. And then as Uday was mentioning, we work very closely with partners and customers to ensure that the best practices are employed, that the best methodologies for getting the most out of the silicon is implemented, and also helping time to market by providing hardened, optimized libraries that customer can just adopt and integrate into their code. Basically, from a FlexRAN overview point of view, let's look at the software part first. So this code is, it's meant to kind of enable partners and get the ecosystem moving quickly and get people in time to market with a quality production level software. So part of that then, of course, is the reference solution. So whether it's the reference PHY on the LTE side, or 5G sub-6 or millimeter wave. These building blocks are all provided as reference. And on top of that, they're modular in kernels, and then they're also stitched together in pipeline. So all that information is provided. In addition to that, FlexRAN test infrastructure is provided. So you can test on a modular level, like block by block, or you can test the pipeline as a whole. We can also do ORAN integration testing, like for the front haul with Working Group 4 to verify that, or we can also do standalone testing of the accelerators so that you can identify component by component performance, functionality, stability, and then you can also see how these integrate together into the system. And so that's kind of what's comprised of the FlexMan software package. Then that gets integrated in with, like I said before, the accelerator card or the NICs, the CPUs to perform kind of a base platform system solution that then runs on the OS or like VMware system solution. So those base components are what RAN vendor would then put their application on, and through our verification and integration and kind of best practices, we get the optimal baseline platform that they can then build on and go to market quickly. They don't need to be concerned with the necessarily the configuration details of these components. They can focus on their specialty of the RAN application. Like I said, the target segments, it's a broad range. It goes all the way from indoor to macro. It's cloud native, fully virtualized, scalable. We'll go through that in a bit more detail in a minute, but basically it covers the full spectrum of use cases. So then working together, how do you make sure that this system and all the work we've done together with VMware, how do we make sure that from all these different components that are related to the OS and the cloud native architecture, how do we ensure that we get the best performance and best stability? It involves many different aspects, including like the CPUs or the BIOS. Let's say, for instance, there's OS controlled parameters and optimal parameters that ensure that the real-time application, right? The base station is a very real-time, low latency application. It needs to be consistent. It needs to be very predictable. And so you can take advantage of, you need to make sure first, of course, that the system is configured correctly, but you can also take advantage of things like power saving states that are provided with Intel CPUs. And in times of low usage or even, windows of opportunity to reduce the power states, you can ramp things down either through frequency or just a lower power state and save, money on that kind of TCO or total cost of ownership. So that's one thing. So we work together to make sure that one is that information is understood, and two, that it's implemented in an efficient way from a system perspective. And same thing with the operating system. There's parameters there to ensure low latency and reliable behavior or consistent operation. And similarly, you can control the power there, and the operating system governor can control when and how things enter more of a low power state. So we work very closely together to ensure that, from a technical perspective, these details are abstracted away from the service provider, from RAN vendors, so that they get the benefits of all these things. But from their perspective, it's very simple to use, it's easy to scale, and kind of the complexity is abstracted away. The same is true for accelerators, which I talked about before. So typically like forward error correction accelerators like LDPC for 5G. These accelerators, they have a whole management system in terms of, bringing up initialization, maintenance, upgrades, field support, things like that. All that has to be tied into the OS and the cloud architecture, so that you can, get the information and metrics that you need, and also take full advantage of all the myriad of features that are provided with the hardware, and ensure that you get, that the customers end up with the optimal configuration. Because there's many different use cases. So what might be the best configuration in one, small cell or indoor application would possibly be different from macro. So that flexibility has to be there, and it has to be configurable in a very simple, easy to maintain way. Similarly, for the NIC cards, those are also provided typically by Intel. There's this, you want to make sure that the interfaces like DPDK drivers are optimal, using the minimal amount of cores and CPU cycles, that the synchronization meets all the 3 GPP requirements and provides consistent timing. So all the years of experience that we've worked together and all the different deployments, we've become, kind of best known practices or best known methods that we like to refer to, have all been kind of incorporated and form this solid base for customers to build upon. And similarly for the other categories, whether it's CPU or just the cloud native architecture itself, physical functions, virtual functions, things that you have to manage and understand, all this knowledge and experience has kind of been baked into or understood and learned through all this integration work and deployments, and now it's available for customers to build upon. And then finally, along the same lines, it's debugging tools or telemetry, just this ability to get information and make it easy for service providers to maintain and the equipment. That's a key concept as well, right? Even though there's this complexity, you definitely want to abstract it away from the end market. And they're based on, like we use common APIs, standard interfaces, things like that, so that it's very scalable and interoperable. And just easy to maintain.
Thank you, Mike. So I'm going to take your slide and those different functions that you mentioned and trying to bucketize them into 3 different sections here. One, functionality required, what are the challenges in the virtualization, and then challenges of putting all the stuff in as an integrated solution. But before I do that, I just also wanted to show this pictorial representation on how the stack is being built. And that also maps to some of the things that I'm covering in the first section, which is functionality required. So as you see here, at the bottommost layer, you have the hardware elements like CPU or the accelerator cards or the NICs and so on and so forth. Then next, when you have the hypervisor layer, which is required for virtualization, cloudification, that also brings in an abstraction, which is a goodness that the applications don't need to really worry about small advances from one processor to another, or not just from the processor perspective, but also some other components like storage adapters and so on and so forth. So, and cloudification actually needs a mechanism to paravirtualize this. So that's the next layer. And then thereafter you have the Kubernetes base OS layer, and thereafter the real Kubernetes control plane. So all these layers have different tunings and settings that needed to be performed. For example, at the bottommost layer, you do expect the BIOS needs to be tuned in certain way that the real-time applications, the latency-sensitive application extract maximum out of the underlying infrastructure. You probably are aware that most server manufacturers do present a latency-sensitive BIOS tuning profile or guide on how to set few things up so that processors don't go to sleep. There are some specific things to tune, avoid SMIs, hardware interrupts need to be steered in a certain way, etc. So that's one, some configurations that are needed to be done on the BIOS level. Then on the hypervisor as well as on the base OS level, you do expect a functionality of real-time processing, which means that this is not a standard enterprise app, right? If kernel is doing something, let it finish and then application will wake up. For L1 apps, for RAN applications, you do expect when a particular frame arrives, it needs to be processed within that stipulated time. Otherwise, you have a problem. So real-time scheduling, the preempt RT kernel patches is one of the fundamental requirements for RAN applications to function. And when you add this hypervisor layer, it needs to be coordinated between what happens in the worker OS and what happens in the hypervisor. Beyond that, you also expect that the applications which are sitting on top have these direct association with actual physical CPU cores so that they don't get interrupted or swapped in and around, and you don't waste any precious CPU cycles around that. Other than just the standard CPU pinning, there are a few other things also that Mike alluded to in the previous section was the additional packages like TuneD, or for that matter even the precision time protocol configurations, or there are PCI utils, etc. that the RAN applications will require. I also kind of mentioned about virtualization, but I want to specifically highlight that although the cloudification and making it available on the as I call it hyperscaler, there is a goodness of bringing virtualization in this mix by abstracting the underlying layer, but it also adds a cost, at least the perceived cost, whether these translations or paravirtualizations, what is the latency incurred because of all that. So that's one thing that RAN vendors as well as service providers continue to ask us, that hey, is that abstraction coming at a cost of my RAN latency budget? So that's the second bucket. And the third thing is all these components, as you saw, processor, then the NIC and the respective drivers, actual BIOS configurations, not just the configurations, but the BIOS versions itself. And then you have the Kubernetes version, ESX hypervisor version, the Photon base OS version. All these are different components, and it is very likely that they will have their own release cycle. And then in a sense, they're all different moving parts. You don't expect the service providers or system integrators, and lastly the RAN application developers, spending time to aggregate this. So there needs to be a solution which provides this continuous integration to validate whether the functionality as well as performance is met. At the same time, allow these individual components to evolve at their own pace. So that is something that we are going to talk. But this is one of the primary requirements as we see, and we think that we are working together to address this problem. We'll talk about it in subsequent slides. So the first thing, although the one that I wanted to address is this common topic that I hear with respect to virtualization or introducing hypervisor in the mix. Of course, hypervisors, as I mentioned earlier, do bring in a lot of goodness, with respect to having this abstraction which will hide the complexity of the specificity of, let's say, storage or network or CPU for that matter from the guest. But then it will also introduce these two scheduler problems or jitter that is introduced by ESX and all that. So I wanted to mention how VMware is trying to address these solutions. So first of all, I want to clarify that ESX is unlike any other hypervisor, which is very specifically and custom built for running both the virtual machines and the Kubernetes pods. It is not a general purpose operating system where you can run any standard application. So that's the first thing. And then the second thing, over last 15 odd months, we have had several advances, and Intel and Mike's team has helped us a lot in giving us a deep understanding on how the RAN applications work and what are their real requirements. So I'll start with how and what are the changes that we have done. So the first and foremost, there are no two schedulers in even if you bring in ESX. So ESX actually kind of pins the respective vCPUs, the virtual CPUs, to the actual physical CPUs, thereby actually completely bypassing ESX scheduler. So you're not going to have a context switch or any shift from one P core to another P core. So with that, you're not going that particular latency of ESX introducing with any of its own scheduling is completely bypassed. Second part, even though I have not captured here, I would like to mention that ESX has also done some specific advances with respect to how the hardware interrupts are steered. They do not interrupt into the RAN applications which are in some sort of a constant busy poll loop because of DPDK. They function in full tickless mode where any of these operations or interrupts do not interrupt. So it allows a complete autonomy in some sense for the RAN applications to take control of that PCPU and run in some sense to completion. While I say that, the typical measurement, if you are familiar with RAN domain, there is a tool called cyclic test. And cyclic test is a good tool to measure what is the real-time nature and overall latency that is introduced by standard timer interrupts, meaning you will fire an interrupt, of course you'll first go to sleep, then fire an interrupt and see how long it took to wake up. In the standard operating systems, you will see that it may vary and it might kind of go from one extreme to another extreme, whereas in the preempt RT or real-time kernels, it is fixed. So in order to understand how this stuff works, again, we worked with the Intel team and we made a lot of advances. So today I'm happy to say that with the advent of ESX U3, the numbers that we observe with cyclic test, and not just cyclic test, the other industry standard tools like OSLAT, the numbers are very, very close to bare metal in the single digit microseconds. And how this is achieved is, like I mentioned, one is steering the hardware interrupts to different non-real-time processors, as are shown more towards the left-hand side of this picture, and making sure that the purple boxes here, which are more dedicated for RAN workloads, are functioning in a tickless manner. And other than that, we also had enabled a few additional technologies from Intel to give the benefits to RAN applications. So in a summary, what I would say is this overall noise, the execution noise, is completely managed and contained. And as we make further strides in the overall hypervisor solution, we provide both best of the worlds, as in we provide the performance, but at the same time we also keep the same security model that ESX has been bringing so far with this provider and consumer separation, where virtual machines as well as the Kubernetes pod get the least amount of privilege that they are entitled to and do not open up the entire system for them. So that was for the part that I wanted to talk for the virtualization. Now the second part I would like to mention is all the different tunings and configurations that one need to employ at the different layers that I was mentioning earlier. One would say that yes, I know what needs to be done, but there needs to be a mechanism which needs to automate or enable this for end users, right? So this is done by Telco Cloud Automation. What Telco Cloud Automation provides you is provide a declarative language or a model to define all the requirements for the infrastructure resources, as well as different components starting from the ESX hypervisor level all the way till Kubernetes, including the intermediate photon as well. So it allows you, in this picture probably it is not clear, but what I'm showing you here is the industry standard HC SOL standard, which is a Tosca template where a RAN application vendor could build a CSAR. CSAR is a HC term, where they can say, okay, here is my Helm chart, and other than what I need to do during instantiation or termination or scale and upgrade, here are some of the additional infrastructure requirements that one needs to also satisfy. And these would include the kernel versions, the preempt RT patch, not just that, but if you want to insert some additional tuned or tuna packages, PCI utils, a specific configuration for tuned, and so on and so forth. The additional examples could also include the SRIOV configuration or a specific DPDK patch, and the PTP configuration that would be required to match the real precision time requirements of DU workloads. So all in all, to summarize, what I'm saying is there is a definitive standard that we propose so that the RAN vendors do not need to know how the stuff is done, but they just define or dictate, this is my declarative requirement, and they just kind of delegate the overall realization to Telco Cloud Automation. This is where we are addressing both Intel and VMware together to build a common pipeline, which is providing a common CI/CD where all these specific components like processors or BIOS settings or NIC drivers and the newer FlexRAN versions, etc., could be brought together in an integrated fashion, this common integration. Not just from the Intel, then because ESX will also continue to evolve. So there will be a separate pipeline to also introduce the ESX components and then our Telco Cloud Automation, and make sure that when they are all put together, the required outcome is still maintained. So the way we do it today is in the Intel labs, we give them the GA code of ESX, and they check whether they have the newer versions, their upcoming in development FlexRAN, as well as the driver components, or even the hardware for that matter. They keep one part constant, rev the other, make sure that it is working to our expectation. A replica of that is also set in our labs, where we take the standard FlexRAN components, we bring in our in development code, validate whether both the things are working together, and if so, then we promote them to next level. Mike, you want to add anything over here?
No, I mean, I agree with that, and one thing I think that is important is just this system view aspect, right? That there's many, as we pointed out through this talk, there's many individual components, and they all kind of need to come together and work seamlessly. So together through this CI/CD lab, we not only verify kind of the individual base components, but we integrate the OS and all these pieces and make sure from a system perspective that this base platform is solid and reliable and meets all the performance and requirements that are necessary for a RAN application.
Actually, one part I actually would like to add is it is not just a pipeline, a joint pipeline between Intel and VMware. We are also partnering with some of the RAN vendors, and very shortly we'll be partnering with some of the server manufacturers also, because there are nuances both from the server manufacturers if they have set up the BIOS in certain way, etc. Even though our recommendations are in particular order, right? When they put all the stuff together, there might be deviations from what we have seen in our lab versus what we have seen in Intel lab versus what they will see in their own labs. So this overall unified pipeline, which is layered with different components, will definitely assist to catch the issues much earlier than later, and then take this forward to eventual RAN applications also, because then they can consume and they can see, okay, the underlying infrastructure is working to my expectation. Now let me bring in my in development RAN code and see whether it is working fine or not, or okay, it kind of vindicates that the underlying platform is looking okay and I need to focus more on my RAN application. So it had helped. I mean, we have worked with some of the partners, and it does look very helpful, at least in our mind. So all in all, what it does, it reduces the overall release cycles for all these components, allows you to get into more frequent upgrades. The CD part becomes very optimal. And whenever we want to do a new RAN vendor certification for them also, it becomes very easy to certify, okay, my stuff works on this specific VMware solution, this specific Intel solution and chipset. So all in all, it provides us a better trusted model to continue to iterate, continue to do an upgrade, and continue to provide these compatibility across different components. With that, I wanted Mike to talk through some of the testing that we have done, and this is more focused from the functional perspective with respect to performance. I talked about the changes that ESX is doing, but unless you actually see how the stuff works and you have the real results, the slideware is just a slideware, right? So, Mike, over to you to talk through the actual results that you have seen.
Yeah, this is a very specific example, but kind of one of the heavier workload use cases where you have massive MIMO, 64 antennas, 16 layers downlink, 8 layers uplink. We can, through the testing, we can control the amount of throughput all the way from the maximum theoretical throughput to average to typical use cases. So we can vary that. In this particular case, we use 100 megahertz cell bandwidth. It's a full pipeline of the layer 1, so all the way from uplink and downlink, the full use case for the massive MIMO case. It's multi-core, multi-threaded, multi-cell use case, and the purpose of this in this particular case is to show, okay, if there's some kind of performance issue or there's some kind of latency or unreliability or unpredictability, the heavier, the more stressful use cases will show that, right? So they'll bring it to the forefront faster. So the idea of this is that it's a pretty heavily cycle count intensive use case, and it's a good one to show relative performance. Okay, so we have many. We have a reference number. We use basically open source Linux, so CentOS 7 based with real-time kernel as a reference, and then we have data with that FlexRAN running on that app OS, and then we also have run tests with VMware ESXi with the Photon RT kernel, and look at the data, right, both from a cycle count perspective and also from a latency perspective. So first of all, if there's some kind of anomaly or kind of a big hit, you would see that it would reflect itself in stability, because basically the system wouldn't be able to keep up with the real-time requirements defined by 3GPP. So that's the first case. But assuming then it's stable for a long period of time, we can go through and look at the data. We have very detailed, I mentioned before, some of those test applications that can profile the uplink and downlink on a modular level, on the full pipeline, looking to see how much each different type of task take. So that it'll highlight if there's some kind of change, you can get a good idea of where the problem might be and what the size of the issue might be. And so when we did this comparison, if you look on the table on the right, first we're talking about core utilization, or this is effectively like cycle count. that there's almost a negligible difference. It's around 1% difference. And so, effectively that using, and as they pointed out, they've done a lot of work to make that performance, as, I guess, optimal. They've made it very efficient, and so that you don't, from a cycle count perspective, you don't notice the difference going from like a CentOS based to a VMware solution. And similarly for the processing latency, this is looking at how long it takes for a task to complete. Of course, if there are multiple extensions, then eventually, like I said, you'll kind of miss the TTI window and miss real time. So here the difference is also very small, around 2 to 3%. And so it kind of depends, how much of that is the budget kind of depends on the TTI, which can vary. But if you're talking about a 500 microsecond TTI, then a 3% difference is about 15 microseconds, well within the range of margin to be stable and hit the performance metrics. So this, achieving these milestones was we worked together, and now I think there's no issues with regard to kind of performance impact with VMware ESXi and Photon-RT, whether you're talking about latency or cycle count.
Mike, I wanted to actually add one more thing over here. See, the numbers that we have done were already within the considerable margin, but I remember that some of our team members are still working this week and next for the newer numbers for the U3. So the earlier slides that I mentioned, where the cyclic test results are now exactly almost similar with respect to when you compare the 5 nines or even 6 nines, the cyclic test numbers are exactly same. So I think it will be very interesting to see when we run this through the U3, it probably will be almost equivalent. So just wanted to give a sneak peek into the upcoming U3 release that we are bringing in, and I'm sure even this 15 microsecond will come down further down to either single digit or even less.
Yeah, that's a good point that I didn't emphasize enough before, is that this is an ongoing effort. It's not we haven't reached the conclusion. There's new hardware and silicon coming out. There's software optimizations on the RAN side, and OS side, basically everywhere. We continue to improve numbers, consistently. We've continued to find better methods, ways to do things, take advantage of new instructions or new features or whatever the case may be. And that's, again, why it's so important to have this, CI/CD framework. So it is a dynamic environment. Things are improving, things are changing. So we need to be able to integrate those changes quickly, prove they're stable, prove they deliver the, performance improvements we expect, and then get them out into the field and get them into production fast. Because it is a complicated system with a lot of different components and a lot of different, things or components to tune, it's very important that we have this automated mechanism to, remove any kind of mistakes in terms of configuration or misalignment or compatibility, and then also to prove the stability and performance.
Well, actually, what we were talking is exactly what is being captured here in some sense, because this integrated offering exactly offers what Mike, you were just talking about. We have this pre-integrated and optimized solution, both from VMware TCP RAN and then FlexRAN solution, which enables the ISVs, OpCos, and system integrators to focus more on what they're best at, like enhance their RAN applications, as well as focus more on delivery. I mean, RAN applications for RAN application developers, but for ISVs and SIs, more focus should be on enabling the markets or providing the solution quicker to their end customers. So all in all, it kind of reduces the overall system development and integration by several months, because you already have this process which you don't need to run several cycles in staging or when you're doing your IODTs, etc. That you reduce that considerably, because the platform is in some sense already ready for you to bring in your workloads and start making calls maybe. Okay, in summary, both the solutions, Intel FlexRAN as well as VMware's Telco Cloud Platform for RAN, TCP RAN, is now ready for deployment. The first version of TCP RAN is already GA available now, and the next version is already in works. Intel and VMware are working together on that. For the first solution, the field trials with major worldwide operators across the continents are already in progress. From the partners' perspective, leading RAN ISVs are already onboarded, and we are also engaged with a few more who are working with us on that front. From the solution integrators' perspective, we are also engaged with many of them, and we are also working in Europe and Asia to help them accelerate the overall adoption quickly. And this joint collaboration development of CI/CD, that is also being extended, like I mentioned earlier, not just between VMware and Intel, but also to the partners, the server manufacturers, as well as RAN vendors, so that they can also leverage a lot out of this and make their life simpler. So that's what we have now. What are the next steps? So the next steps are both VMware and Intel will continue to evolve and take benefit of this rapid integration process that we have through CI/CD. And we will continue to make this available through not just for what we are doing, but also the other components with respect to BIOS and firmware, the next advances in processors, NIC, memory, etc. Also in the Kubernetes world, as well as what VMware brings in from ESX and overall platform. So that will continue to have the same alignment like we have had before, and all of this will continue to operate in the same new cloud native world, also covering the better diagnostic debugging tool like we mentioned earlier. Other than this, we also, I want to mention about one specific area. Other than the platform initiative, we also have been working together on the RIC and XApp developments, which is more on the ORAN side of the world, where we do this joint integration for the common RIC platform. And I will strongly encourage you to go in and listen into some additional sessions that we will have on the VMworld front. So thank you very much for listening in, and I strongly encourage you to also reach out to us if you have additional questions or any information that you would need. Thank you.
Yeah, thank you for listening. The vRAN transformation is an exciting journey, and there's a lot more innovation and exciting steps coming forward.